A new technique confirms the universe is 69% dark energy, 31% matter, mostly dark. How much stuff is there in the universe? You'd think it would be easy to figure out. But it's not. Astronomers add up what they can detect, and still find there's more to the cosmos than they see. So, what's out there, and how do they account for it all? According to astronomer Muhammad Abdullah, National Research Institute of Astronomy and Geophysics in Egypt and Chiba University, Japan, the universe has dark and visible components. Matter only makes up 31% of the known universe. The rest is dark energy, which remains a major unknown. Cosmologists believe that only about 20% of this total matter is made of regular, or baryonic, matter, which includes stars, galaxies, atoms, and life, he said. About 80% is made of dark matter, whose mysterious nature is not yet known but may consist of some as yet undiscovered subatomic particle. Determining the makeup of the universe using galaxy clusters. The best measurements of the stuff of the cosmos come from the Planck satellite, which mapped the universe. It studied the cosmic microwave background, the remnant radiation left over from the Big Bang, some 13.8 billion years ago. Planck's measurements allowed astronomers to come up with the gold standard measurements of total matter in the universe. However, it's always good to check against Planck using other methods. Abdullah and a team of scientists did just that. They used another method, called the cluster mass richness relation. It essentially measures the number of galaxy members in a cluster to determine the mass of the cluster. According to astronomer and team member Gillian Wilson, it offers a way to measure cosmic matter. Because present-day galaxy clusters have formed from matter that has collapsed over billions of years under its own gravity, the number of clusters observed at the present time, the so-called cluster abundance, is very sensitive to cosmological conditions and, in particular, the total amount of matter, she said, noting that the method compares the observed number and mass of galaxies per unit volume with predictions from numerical simulations. It's not an easy method because it's difficult to measure the mass of any galaxy cluster accurately. Much of the mass of the cluster is dark matter. In other words, what you see in a cluster isn't necessarily all you get. So, the team had to get clever. They used the fact that the more massive clusters contain more galaxies than less massive ones. Since all the galaxies have bright stars in them, the number of galaxies contained in each cluster is used to estimate total mass. Essentially, the team measured the number of galaxies in each cluster in their sample and then used that information to estimate the total mass of each cluster. Matching Planck. The result of all the measurements and simulations nearly exactly matched Planck numbers for mass in the universe. They came up with a universe that is 31% matter and 69% dark energy. It also seems to agree with other work the team has done to measure galaxy masses. To get their results, Muhammad's team was able to use spectroscopic studies of clusters to determine their distances. The observations also allowed them to tell which galaxies were members of specific clusters. Simulations were critical to this work, as well. Observations from the Sloan Digital Sky Survey allowed the team to assemble a catalog of galaxy clusters called GalWeight. Then they compared the clusters in the catalog with their simulations. The result was a calculation of the total matter in the universe based on the mass richness relation. The technique is robust enough for use as new astronomical data arrives from various instruments. According to Wilson, the team's work shows that the MRR technique extends beyond their work.